Welcome back, everybody. So we are going to continue where we were. You remember that we looked at the hardware. So now you know what there is in a data center. You know, whenever you use the web or services online, then you know what's actually going on behind. And now we are going to look at a logical model for S3. Again, data independence. It means that very often in this course, I'm going to look at the logical level without worrying about the physical details. And then we go into the physical details of the system. But not S3 because Amazon didn't tell us how they did it. But I will do it with a little bit with Azure Blob Storage. Okay, so here's the S3 model. In S3, you have something called a bucket that has a bucket ID. When you select a bucket with the bucket ID and you look inside, there's objects with an object ID. Yes, like ChatGPT, you can complete the sentence. Very good. So bucket IDs and object IDs. That's it. That's the logical model of S3. That's all that you need to know for the logical model. What strikes here is the simplicity. Super simple. Bucket ID, object ID, and you have your object. The next thing is that there is a limit on the size of the objects. You cannot have an object that has a size above 5 terabytes. To remember the order of magnitudes, because this is the order of magnitude that matters, 5 terabytes is basically something that barely still fits on a hard drive today, right? If you, I'm not talking about the super expensive 245 terabyte hard drives, but the ones that you commonly have on computers, right? So I think many of you will have 1 or 2 terabytes. Who has 1 terabyte of hard drive on their laptop? 2 terabytes, right? That you find 2. Above 2, maybe at home on your computers. Who has 3, 4, 5? Ah, we still have people with 5. So you see, you can store S3 objects on your hard drive. This is the order of magnitude. That's how you remember it, right? So the typical size, the upper end of the average disks that we have today. Another limit, which is technically not just a limit, maybe an economical limit or to keep things under control. As a user of Amazon, AWS, you can have up to 100 buckets per account. You can actually have more, but you need to write to them and explain why you want more buckets. Typically, if you're in that position, you're typically a PhD student who's playing around with buckets and needs more, so they're used to it, and they typically say yes, but they need to keep it under control. Maybe I need to open a parenthesis. Maybe people would not be surprised today, but I remember a couple of years ago, some students came to me at the break and asked me, why are you talking about Amazon and the cloud? Like Amazon is selling books, so why are we talking about Amazon? Who was surprised of hearing of Amazon? Today, maybe less, right? Because now it's a bit more known that Amazon actually has it's called AWS, Amazon Web Services. And Amazon is not only selling books, they are also renting computing power and have a whole clouds. The main competitors being Azure and Google. We also have OVH Cloud and some other providers in Europe. Where am I? Yes, so these are the limits. Now I need to do a bit of legalese, like lawyers. Speech. So you know that when you use a system like that, you have a contract, a business contract with, I imagine you're a company and you're using these services, and you need a few guarantees because you pay for it, and so you need a few guarantees. And so now I want to tell you a bit what it looks like in this sort of contracts. That's typically called a service level agreement, SLA. And what's really the main feature of these contracts is that they have a lot of nines. In there, right? So like here we have 99.9999999%. And that tells you here that you have a probability of 99.99999% of still having the object 1 year from now. What that means is that if you stored 10 to the power of 11, that's about 100 billion objects in S3. It's a lot of objects, but if you store the 100 billion objects, then you're typically going to lose on average one of them every year. That is just corrupted and goes away. Okay, so this is part of the service level agreement that they give you that guarantee that this is the loss every year. Of course, it's fine because when you have a guarantee like that, if you're not happy, what do? You just Oh, you sue? Yes, of course you can sue, but but before you sue, if you have this guarantee and you want maybe to lose less than that, there's another solution than suing. Before that, what can you do? Redundancy, yes, exactly. Just store two of them. Every object you store twice, then you can compute as an exercise the new probability of losing logical objects, and that's improving. In fact, it's the same thing in quantum computing, the difference between a physical qubit and a logical qubit, because the physical qubit can make errors. If you have a logical qubit with multiple physical qubits, then you improve the results. All right, so SLAs with lots of nines. All right, and to remember the nines, I think one of my TAs showed me there was a viral video of I think it was a professor at ETH that students asked questions and she answered 99999. So this is how you remember this slide right here. This is pretty much this. All right. Now we use the nines for plenty of other things, and another one is availability. That's about how much time every year the system is down. And if you say you have 99.99% of availability, then it means 1 hour every year, max, the system is not available. I have a table for you. Oh yeah, all the nines. I have a table for you that summarizes, just to give you orders of magnitudes. And you see if you have a lot of nines here, you're already 4 seconds a year. So of course, the lower, the better, but also the more expensive. So this measures availability always with nines. How do you measure the guarantees on response times? Also with nines. We have a question. So we are going to use this little microphone right here, which is kind of cool with the cube. We just need to throw it in little hops to make sure that it doesn't land on somebody by surprise. So let's go ahead. Where do we want it to go, the microphone? Who is raising their hand? Or do you no longer want to ask the questions because now all the attention is on you? Yes, over there. So maybe we can throw it. So please help. Maybe small hops. You launch it here. Yes, exactly. And then you throw it in small hops over there. Yeah, exactly. That's the idea. Go ahead.
I had a question, but about a previous slide. If there's no limit to how many objects I can put into a bucket, why would I need more buckets?
Ah, yes. You could, in fact, what you mean is you could just have one bucket and store everything in there, right? One aspect maybe would be organization, is that typically you create a bucket for a specific purpose. To give you one concrete example, as we'll see later, you can create a bucket for a website and a static website, and then you can put, thank you, you can put all the files in there. And so that would be one reason to use a bucket for a specific thing. So it helps you keeping things organized. Another aspect is performance, and that one is a bit tricky because normally, if you have plenty of objects in the same bucket, that doesn't lead to any performance drop in terms of queries, but in practice it does. And that's something we know because one of my colleagues here at ETH at some point was experimenting, pushing again the systems with it, to its limits, which is really cool PhDs to actually do these kind of things. And then he noticed that with a very large number of objects, performance started dropping. And so he wrote to the support and so on. And what he found out is that having multiple buckets actually solves the problem of the performance drop. We don't know why. It was just a very empirical thing that he realized, right? He was the former head TA of the course, Ingo Müller. All right. So all these nines for the SLA. And for response times, we also like to measure them with plenty of nines. That doesn't mean that the response times have to be numbers that are made of nines. It's just that we do it differently. instead of telling you, we guarantee you a response time of 9.99 milliseconds, response times vary, right? Can depend on the situation. So instead, what we do is we give you a percentile. We tell you, we guarantee you like 10 milliseconds in 99.9% of the cases. So it means that out of 1,000 tries, 1,000 requests, only one will take more than 10 milliseconds. The others will take less. So this is again the SLA, the service level agreement language that always uses these cool numbers. Okay. So this is it for the legal part of these agreements. And by the way, about suing, of course, you can sue if you're unhappy. But generally, there's very great videos, by the way, I remember one from Stanford about negotiation and negotiating contracts. Normally, when you negotiate contracts, you're trying to find people you trust. And then you establish a relationship of trust. And the goal of a negotiation and of an agreement is that people enter a long-term relationship. And so you don't want to make a contract to then sue. What you want to do is find a good contract that you can keep in the long term. All right, I'm a bit getting away from the course topic. All right, but some of you create startups, so it can always be good to have a bit knowledge outside of just technical. I'm going now to study something else, except if there's questions. Yes, there are. No questions? On Zoom, do we have questions? We didn't have any question on Zoom so far. You know, you can ask questions. You can write in the chat, and Dalia will read it for you. No questions on Zoom either? All right, we are going to break the ice. We already broke it in the lecture. Some people are asking questions. All right. By the way, a little trick that I know some of you used in the previous years, I know that some people in the lecture hall ask their questions on Zoom. That they don't have. That's totally fine. You can absolutely do that. It's totally fine. You really need to remember when you ask a question. I was a student myself, you know, and even when I ask questions, I'm always afraid, like, am I going to ask a stupid question or something that was already explained? But the thing is, very often when you ask a question, half of the room is very happy you did because they had the same question. They just did there to ask. So it's always fine to ask questions. So I'm going to continue now to the CAP theorem. Whoever heard of that? Who never heard of the CAP theorem? All right. So you might remember ACID, right? ACID guarantees, right? Availability, atomic consistency, isolation, and durability. These are the guarantees we have with a monolithic relational database management system like PostgreSQL or Oracle, IBM, Microsoft. What we would have liked to do, but we didn't manage, is to have ACID also for big data. For 500 petabytes of data, we also want to have ACID. The problem is it's very challenging. We just cannot do it right away. And so this is why, in the very beginning of big data, the idea of ACID was dropped. We just give up on that. It's actually coming back, and now there are people again pushing for ACID, but we're going to go chronologically, right? So first, we are going to study what happens when you drop ACID. And when you drop ACID, you enter a different territory that is governed by the CAP theorem. The CAP theorem is an impossibility triangle. It means that out of 3 things, you can only have 2. And CAP is exactly the initials of consistency, availability, and partition tolerance. So you can only have 2 of the 3, and that means that there are CA systems, AP systems, and CP systems. So every time you have a system, you can ask yourself which ones of the 3 does it have. One other way to formulate it, so here it was the symmetric formulation. If you want to put it in a less symmetric but more intuitive way, that basically means that if there is ever in your system, which is in a data center with plenty of machines, maybe even all over the world, if there is a partition, meaning your network is split into several parts, if there is a partition and you want to be tolerant to that partition, meaning you don't crash, you continue functioning, then you have to make a choice. Either you become available, but you lose consistency, or you remain consistent, but you lose availability. That's what it means. A network partition forces you to choose. So what do they mean? Atomic consistency. Oh, by the way, I made a mistake. In acid, it's not atomic consistency. That's consistency. The consistency in the CAP theorem is not the same consistency as in the acid framework. In the acid framework, relational databases, consistency means that your table or your data is in a consistent state. If you have integrity constraints on your schema and so on, then in between transactions, it's always fulfilled. That's what consistency means. What we mean here in a big data system, in the CAP theorem with consistency, that's why I put atomic consistency, which is another kind. It means that if you make your request from different machines, because you have many machines, so you could make a request to several of them, you get the same results, right? All the machines will agree on the answer. If you try to get an object, then all the machines will give you the same object contents. That's consistency. For whom is that clear? Right? Okay. And if you fail consistency, that means that what you get depends on the machine. A machine might give you some value and another might give you an older value, perhaps because it's not aware of a newer value. So that's consistency. Availability means that the service remains available. You continue to deliver the responses to the requests. You don't basically tell people come back in 5 minutes, right? So available means you continue to give answers. Network partition, and now I have a small animation. Network partition means that, so let's say these are all the nodes, right? The machines, I told you, they're also called nodes, and so I can even represent them as actual nodes in a graph. This is the network topology. Of course, that's more complicated in reality. But as an example, these are your nodes. And imagine that there's an earthquake or whatever natural catastrophe, and then the system is working, and maybe somebody updated a value right there. Maybe they wrote a comment on LinkedIn, or they uploaded a new object to S3, and then that needs to propagate to the rest, right? But while it propagates to the other machine, there might be some partition. The network might break. You lose the connection to parts of the system, and this cannot propagate all the way here. And this is a network partition. And here you have the choice between two possibilities. Possibility number one, you insist on being consistent, so then you have no other choice than to temporarily stop giving responses. You stop being available. You say, sorry, you have to wait. Please come back a bit later. That's possibility number one. It means you are CP, right? You're CP. You decide to no longer be available. You are C because you're still consistent. And why are you P? Because you don't crash. That is the difference. You don't crash. The system politely and smoothly tells, please come back later. So it's partition tolerant and consistent. Possibility number two is you say, okay, I don't crash. And I accept to give inconsistent answers. So that means I'm still available. I still give answers. But then the people who ask on that side, they will get the newer value, the latest one. And if anybody connects here instead, they will get an older value. Then do you agree it's no longer consistent because you're delivering different responses, but you're available? That system would be AP, right? So who understands CP, AP, right? Okay, very good. And a system that would be AC, but not P, means that it just crashes and that's it. It stops functioning completely, it crashes, you can't recover. That would be a system that is not partition tolerant. For whom is that clear? Yeah, all right, so AC, AP, and CP. Now there's something very cool, and actually it's some students in previous lectures that may be aware. There's an even more general way to look at it that generalizes the CAP theorem. It's the, I don't know how to pronounce this thing, like PACELC, PACELC, so that's an extension of CAP. It starts in the same way that basically tells you in case of a network partition, if suddenly it breaks, and you have to make a choice between being consistent or available. And in a normal case, where it doesn't break and there's no partition, you also have to make a choice. Either you're consistent or you're low latency. Low latency means the responses are very, very fast, right? So you have to make a choice. And the idea is that there's a trade-off here too. If you want to be consistent, you need to be a bit slower, right? And why? Because you need time for the information to propagate. For whom is that intuitive? Okay, so that gives us 4 kinds of systems, right? All these 4 systems. Now a bit of warning. Something happened in the past few years that there was the first paper released claiming we have C, A, and P all at the same time. And then other companies followed and said, okay, we also have CAP. And everybody said, okay, we also have all of CAP. Don't fall for that. Because the trick, it's a marketing trick. When they say we have all of C, A, and P, what they really mean is that since network partitions are so rare anyway, then we're all of that, right? So that's it, because you're consistent and available when there's no partition. But the problem is that on the day that a network partition is going to happen, then they'll have to make a choice. It's just the laws of physics, right? So be very careful. Any claim that it's CAP at the same time is a marketing claim based on the fact that you consider network partitions to be rare. We have a question or maybe an observation over there. Yeah. Small hops. Yeah, very small hops. Yeah, careful not to surprise anybody with this directly arriving on their head. Yeah, go ahead.
This is bigger. Okay. Can you repeat again, why do we partition? Why do we have network partitions, and what's the benefit we gain from those?
All right, so a network partition is not a benefit, right? So you're not happy about having a network partition, but the network partitions happen. And so when a network partition happens, your system has to make a choice between 3 possibilities. Possibility number 1, you just crash and you don't recover. Possibility number 2 is you tell people to wait and come back later when the partition is gone. Possibility number 3 is you continue to serve everybody, but you just accept that some parts of the system might be stale with old data. Does it help? Awesome. We have another question.
Yes. If the system crashes, how is it still available?
It's not. It's just not partition tolerance. Then you could claim technically. Then you get into almost a mathematician thing that when you have a universal quantification on the empty set, it's always true, right? So if you just don't even resist a network partition, then you can claim that you're everything just because you crashed. But this is more like I would say abusing the symmetry of CAP. The idea is really just you crash and then you call it AC, right? And again, the intuition of calling it AC is that when it works, it's both available and consistent. That's why it's called AC. Does it make sense? Right? Okay. So again, the trick to understand CAP is to see that it's really, you instead of looking at it symmetrically, just formulate it as if a partition hop happens and I want to continue functioning, I need to make a choice between available and consistent, or I can crash. Does it help? All right, another question?
We have a question.
Oh, on Zoom, let's go to Zoom. Yes, yes.
For the CAP theorem, which trade-off do systems like Amazon S3 choose, and which 2 properties do they choose to satisfy?
Mm-hmm. So that's going to be different for every system. That's what basically I told you. A few years ago, there was an announcement on S3 that they're all 3. And the analysis, when you look at what people were saying, is that it's because network partitions are very rare, and as long as it doesn't happen, you're everything. So the answer to that question, as far as I'm aware, is we don't know. And one day there might be a network partition for some reason, and then we'll know. So that's how I would answer it.
Thank you.
So yeah, I would just be very careful with the claims that that systems are all 3. This really just means network partitions are rare enough that you don't need to worry about them. Okay. Any other question? Okay, no more raised hands. Over there? No, that's not a question. Okay. Are you happy with the answer on Zoom?
Checked,
Yeah.
and the person just said yes.
Okay, yes. So I want people to ask more questions. So I want to satisfy their questions. Okay. For this thing to work, I still need to activate a specific window. So I have it here. Okay. So that's the CAP theorem. If you have a network partition, you need to make a choice, consistent or available. And in normal cases, you need to make a choice. Either you're consistent or you're low latency. Very quick answers. Which is now the CAP theorem. So now I'm moving on to another part, if there are no more questions. REST APIs. Whoever heard that? Who never heard of REST? Okay. REST means representational state transfer. It's scary, but what it really means is that you use HTTP the way it's intended to be used. That's basically the summary of REST. It was a PhD thesis that was done already a while ago. Why is that important? Because it has to do with how you use a technology. S3, HDFS, HBase, MapReduce, any technology. You use it in some way, you connect to it in some way, and these ways, it's very generic here, not just S3. Maybe you connect to it via a terminal. You can access Amazon services via CLI, via terminals. Or maybe you want to use a programming language, Java, Python, R, and you connect to it via an API in a programming language. Or maybe you connect to it via a Jupyter notebook. You install some magic and then you just write in the cells. Or you connect to it via HTTP, via a network protocol via HTTP. So I need to explain, well, I'm not going to explain HTTP because you're computer scientists and you already know what that means. But I'm just very happy that it was invented right here in Switzerland, in Geneva. So that was the invention of the web by Sir Tim Berners-Lee. It's basically whenever you open a browser and the page is displayed. But if you only think of it as opening a browser and typing an address and seeing a page, then you're only seeing half of the picture. Because this is the case where a person communicates with a machine and gets information from the internet. But HTTP can also be used for machines to communicate with machines. Then it's not a browser, there is no browser, but the protocol is the same. You're shipping queries, HTTP queries. So I'm going to quickly explain that to make sure that everybody is up to date with what that means. HTTP and REST, which is using it strictly, is made of two concepts, just like buckets and objects for S3. So here the concepts are resource and methods. A resource is something that you want to interact with. Could be a web page, an image, a video, a file. Could also be a light bulb that you want to switch on just because you can, or it can be a car, or whatever resource. Could be a real life object like Internet of Things. So you want to access that resource, and to access that resource, you need to identify it. And the way you identify it is called a URI, Universal Resource Identifier. That I'm sure everybody who heard of URI. Right? Most people. You might have heard of URL, Universal Resource Locator, and URN, Universal Resource Name. This is obsolete. Nobody says URL and URN anymore. The general public, yes, because it's still popular, but normally it's no longer supposed to be used. Now we just say URI. And in fact, even URI shouldn't be used. But the problem is that everybody uses it, so I still say URI. What we should be saying, and nobody does that, is IRI. International Resource Identifier. Nobody ever says that. I never hear anybody say IRI. So in practice, just everybody says URI. Okay, URI, Universal Resource Identifier, looks like this, what you have in your browser, and it's made of a scheme, an authority, so that's a domain you own, a path with all the slashes. Then you have a query part after the question mark. Originally, it had to do with JavaScript forms when you transmit that over the get method. Then you have a fragment with a sharp sign, or a hashtag, as we call it these days, which in a browser just jumps to a specific part of the page. But when you use REST, that doesn't really matter. It's just a technical possibility, right? You can just use any string that looks like this. HTTP, there's also FTP, mail2, HDFS, S3, S3A. There's plenty of different schemes that you can use. For whom is that clear? All right. This is a resource identifier, page, image, light bulb, car, anything. The second thing, before I move to the second thing, the methods, in S3, if we think of S3 specifically, then this is an example of URI that identifies a bucket that has the name bucket. You just need to replace that with the name of the bucket ID. And this might also be the region, because you can have multiple regions, EU West, EU East, US, Asia, and so on. And then this is for an object. You also have an object needs the bucket plus the object, so the bucket ID plus the object ID. And that gives you the URI for the object. Okay? And so whenever you have a REST API, you just have a convention on what the URIs are for everything that you manipulate in your program. In the case of S3, that's buckets and objects. All right. The second part is the methods. A method is a verb, an English verb. A few of them are shown here: get, put, delete, post. There's others. There's even extensions, WebDAV, I think it's called. But we'll just look at these four. So get, put, delete, and post. Now, before I look one by one, I want to say that whenever you communicate over the internet using the HTTP protocol, you always have a request and a response. In the request, you specify get, put, post, your URI, and a bit of information, some header, body, and some parameters. And you get a response with a status code. The most famous one that everybody knows, even non-computer scientists, is 404, obviously. So you see how it's made it to popular culture. And then we again have so here it would be the web page or the image. Or if it's a light bulb, this is not the light bulb you have in here. You cannot ship the light bulb over the internet. Instead, what you communicate is a representation of the state of the light bulb, right? So always some representation of the resource, technically speaking. Now, this is a real life. This one I don't show in big data for engineers to not scare people, but since you're computer scientists, I can show you that. This is a real request, what it looks like. This is what a browser might send. Actually, it sends more than that. Then you get the status code that 200. Oh, it worked. 200, okay. Then the headers and then the HTML page. Okay, so that's a concrete example. You see in the end, it's just text shipped over the network. All right. So what do the methods do? Well, technically, you can make them do whatever you want because you can program it in any way you would like. So when I say they behave in a certain way, it's a convention that it's recommended that you respect that convention whenever you implement a REST API. And in exchange for that, you can expect that the REST APIs respect these conventions. So the convention with get is that it's supposed to be side effect free. When you get a representation of a resource, it's not supposed to change. So if you say get on the light bulb, it's not supposed to switch it on, right? It can tell you if it's on or off, but it's not supposed to change it. The one exception tolerated would be logging. If you log to some place the requests that are made, but that's not considered a side effect from the perspective of the system functioning. Put is going to upload some representation of the resource that modifies it. If you, for example, put some XML or JSON or some file or some object content to S3, that's going to replace or create the object at that position, right? So this is put, and it's expected that when you do put and then get on the same URI, you're supposed to get back the same thing, right? For whom does that make sense? Right? Okay. When I say the same thing, you also need to know you can have parameters. You can do a get and say, oh, I want JSON back or I want XML back. So you can still have a few parameters to adapt. But anyway, put and then get. It almost feels like a key value store in a way. We'll get to them. Then you have delete. You delete a resource. And so the expectation is that if after delete you do get, then you get. What error? What status code? 404, exactly, right? That's expected. After delete, you get a 404 with a get. Post is basically everything else. Everything that you can't cover with the semantics of get, put, delete, then you use post. That's what all systems do. So post is very, very generic. At some point, there was a protocol, I think by Microsoft, called SOAP. Who heard of SOAP? All right, so SOAP uses just post everywhere. The problem is cybersecurity. It's very hard to configure firewalls when every request is just always post. So that's one of the objections. But anyway, that's not working? Yes, it is. So now if you look at specific APIs like S3, then you have a way to interact with S3, you create buckets, you list buckets, you create objects, you download objects, you delete buckets, just with the REST API. It's very powerful. You can also do it with calendars, with HDFS, with database systems. So many systems support the REST API. I think this thing is getting tired. I need to press multiple times. Now, how do you use the REST API? Well, the answer is simple. You just need to look at the documentation of the system. There is usually somewhere a place where it's explained. In the case of S3, you can find it online. There's a page that gives you the way it works, and you have the list of everything. There's a huge list of things you can do with the buckets and with the objects. And they give you examples. So here, put, this is create a bucket, right? So creating a bucket can be done with a put request on a specific URI, right? And so typically, a documentation is going to give you information on what you can do, what methods you're supposed to use, what the resource, what the UIs look like, what status codes you get, what they mean, and what you're supposed to do if you get them. Who is with me? Right? Okay. So this is REST, and in fact, REST is HTTP used in a strict way. What's the lesson here? So first, as a user, you can very often use a REST API, but the reason why REST APIs are so important is that when you have a system like S3 or HDFS, you might be using it from different languages, Python, Java, C++, and so on. Imagine all the resources that it would take if you need to create a binding or a driver for every single language that there is. Right? That would be very resource consuming. What can be done in practice is that instead you write a REST API once and for all that anybody can connect to via HTTP. And then when you create the language bindings to connect to it, you just have very lightweight implementations that just connect via REST. So it's a very good architecture to make your system reachable by many, many different languages. For whom does that make sense? Right? Okay. Right. So now a few more things, because we are reaching the end, but I can give you a few more aspects of S3. First, I told you it's flat. It's completely flat. There's just object IDs and bucket IDs, and you get the resources. But then you might object, okay, but then why do we have slashes in the object IDs? And it looks like we have hierarchies and so on. Like when you host a website, you still have the path and so on. So what's going on here? Something's not right. So what you need to understand is that these paths are simulated. From a physical perspective, in S3, the slashes are just symbols like any other, right? So this is an object ID, this is an object ID, this is an object ID, right? So it's structured like this. But for convenience, you can interpret the slashes as paths. And when you go to the user interface, there's plenty of user interfaces to S3 and such systems, you see a hierarchy like this, but it's more like an emulation of a hierarchy this way by interpreting the slash in a certain way. Again, physically, the way you store things, you just have object IDs and they are just maps to the objects. The second thing, although I already mentioned it, systems like S3 or Azure Blob Storage or Google Cloud Storage are very convenient and popular for very cheap static websites. If you need to set up a website without any dynamic content, no PHP, no database system, anything, just static, just have an HTML page that never changes and images that never change, then you can use that because it's very cheap. And so an example is that the JSONic website is on an S3 bucket. It's just all static. Okay. S3 is also very popular with streaming, like Netflix, all the providers. They all use systems like S3, Google Cloud Storage, Azure Blob Storage. Typically, all of them, because that gives a bit of redundancy, right? So many use several systems. And so the trick of a streaming service like Netflix is that the computer downloads the chunk. So the movies are divided in very small chunks. You download a few seconds, you play it, and then when you see that you're slowly reaching the end, then the computer downloads the next one. If it sees the network is very slow, then it can request the next one in a lower resolution. Then you see on your screen that in real time, suddenly the resolution changes or improves or gets worse. This is because when you stream, in fact, what you're doing is downloading very small chunks from S3, Azure Blob Storage, Google Cloud Storage. Right? So maybe that demystifies a little bit what happens when you watch your favorite series. Now you remember this goes over these systems with objects, S3 objects that are actually the chunks of the series you're watching. But of course, it's big data, so I cannot also say that you can use that for storing data. And in fact, what is very commonly done is that you store your data. Typically, what you're going to have with a lot of data is some directory, and then your data is going to be spread over plenty of objects because the data set can be more than 5 terabytes. And so you're just spreading it over hundreds or even thousands of different objects. And we'll see that these objects can then be accessed by the whole data center in parallel. So that we'll see when we study MapReduce. But it's very, very common to have data sets stored like this. Again, because per byte, the storage is very cheap, like this. Yeah, that's the last slide before I stop. Very quickly, you can pick how much you pay and how much you get from it. If you use S3 just to back up your data, probably you don't care about real-time access. So then you can pay a cheaper price, like Amazon Glacier, I think it's pronounced. And then you agree that it might take a couple of hours to get an object, right? If it's just a backup, then maybe that's acceptable. Then it can be stored on tapes. You know that tapes still exist. They are the cheapest way to store ever. ETH still has them to back up your data on ETH servers, and there's little robots that can go get the tapes in a couple of hours to give it back to you. Okay, so this is where I stop for today. We are going to continue tomorrow. Very quickly, I'll talk about another one, Azure Blob Storage, very briefly. Then we'll look at key value stores. Thank you very much, Dalia, for moderating. Thank you for coming. Thank you, and I'll see you tomorrow at 9 a.m.